Okay, so now we can talk about flow boiling. Are there any other questions on pool boiling before we move on? Okay. All right, so I mentioned there's two kinds of boiling. One is pool boiling. It's just a pot of water sitting there. The only movement is due to natural convection, movement of the bubbles, basically. Flow boiling is when we're forcing liquid through, and then we have both phases moving at the same time. So let's maybe draw out a schematic here of what this might look like. I'll do it a little bit more quickly than the last one, just because you kind of get the idea now. But some important things. So first of all, I'm going to draw an arrow down. This is G. This is our gravity. So there are different correlations that you can use for flow boiling depending on if the tube is horizontal versus if it's vertical. So in this, the way I'm drawing it now, gravity is acting down. This is a horizontal tube. So into this system, we have a subcooled liquid at some temperature, let's say a few degrees below the saturation temperature. And so what I'm going to do is, let's assume that the entire domain here is like liquid, except for the little regions that I draw as bubbles. Okay, so just imagine that it's full of liquid except for where bubbles are. So in this, we are, let's say, applying a heat flux. So we're like applying a heat flux on the outer surface along the entire length. So heat is being added. All right, so first what happens is right away you're going to get very near the surface, little bubbles forming. Okay, so it's not until maybe about this point, and these are like just qualitative, right? I'm not telling you that there's a certain fraction, but qualitatively, you're getting bubbles forming, they're getting bigger. It's not until like at this point at which the entire flow achieves saturation temperature. So you're kind of subcooled, even though you're starting to form bubbles, because right at the boundary layer, you have this heat flux, you have like a temperature gradient, you have boiling right near the surface while the rest of the fluid is heating up. So Tsat, this sort of occurs a little bit in, and then at this point, you start to get these bigger bubbles that are forming, like this. So there's a mix of bigger and smaller bubbles. There's some smaller bubbles on the bottom. You might get a bubble that sort of moves up from the bottom to the top, but you have a difference between the top and the bottom. And that's because of gravity, right? Like the liquid wants to stay on the bottom, the bubbles want to stay on top, just because of the density difference. Okay, so this is called, let's see. So this is called the churn region, where this is occurring. And then it sort of just gets more and more. So like at some point now we move into this region where the bubbles get big enough that you actually start to get this kind of annular region, this region inside that is occupied entirely by vapor. So this is down here, the annular region, and that's called annular flow. All right, so maybe we can just draw this a little bit more dramatically. So you're getting the bubbles sort of move and they merge in with this central region. And like, I guess you maybe wonder why this is occurring. So what the annular region is this collection of steam vapor that's moving at a higher velocity. So, well, maybe it's obvious, but why would it all be at the middle? Well, it's because there's shear stress between the wall and the flow. And so that shear stress is going to kind of want to hold on to the liquid while the less viscous vapor just sort of shoots through the middle. So you get this kind of ring around the edge of a liquid that's forming, and then you have this steam that, or whatever it is, the vapor, that's, like I said, the annular flow region. So we just sort of call it there. And one of the interesting things here is this point where you have kind of annular flow developed, let's say right here, corresponds to a quality that is like a mass fraction of vapor of about 3%. Okay, maybe a little surprising. So I'm saying like if 3% by mass of my fluid is vapor, I have annular flow. So it doesn't really take that much heat addition to develop this annular flow. And that's because, I mean, obviously vapor is that much less dense than liquid that it takes up that much more space. So the other thing is like as you're going through this down in the x direction, the velocity is increasing and increasing because the average density is decreasing, okay? Okay, so now we have this like region, we've got these, this annular flow occurring. We start to get like little bubbles or droplets of water that sort of break off and shoot down the middle as well. They're eventually resolved or eventually evaporate. But this region here is called the spray annular. Okay, so you get, you get these vapor or liquid droplets that are entrained in the vapor. They just fly along and kind of interact. Eventually, you start to have what's called dry out occurring. So let's say, let's see like this. Draw a few more vapor. So you have dry out occurring. Dry out is when now there's no longer this phase change happening at the wall. So all the liquid is now evaporated, for sure on the top, right? Because the liquid's going to want to flow to the bottom. For sure on the top, you have a little bit of droplets remaining, and the bottom is sort of also drying out too. So this dry out region is kind of the last thing to happen. Dry out here. And then beyond this would be like any superheat. So this is where your vapor now starts to go beyond the saturation temperature. Okay, so this is like anatomy of boiling flow. Any questions on this? Yep.
How much heat flux needs to be added to make this happen? Does it have to be like a very large heat flux, or could it happen with like just a small temperature difference?
Yeah, so the amount of heat flux, I mean, if you're adding heat to flow, to a pipe or duct or whatever that contains a liquid that's near saturation, that heat has to go somewhere, right? So, and it will go into forming bubbles. If you have a very, very long pipe, I suppose this would just be stretched out over the entire pipe. If you have really low velocities, that is like you have a really low heat flux relative to the diameter of the tube or whatever it is. Your annular flow is really going to kind of be mostly liquid on the bottom and maybe steam on the top. You don't really get an annulus, you maybe get stratification. But this, I would say, for most reasonable boiling applications is what you're going to tend to see. And again, like you're providing this flow in, and it's maybe not a large velocity to begin with, but by the time you're at this annular region, it's really moving because you have a lot of steam that is low density moving through the pipe. Good question. Anything else? Other questions? Okay, so this is flow boiling. Let's see, then to give you correlations, this will be the last thing. So this is one example. There's actually a number of correlations for flow boiling. This is one example called the Shaw flow boiling correlation. And what this does is it formulates things in terms of three non-dimensional numbers. And that is, let's see, let me write out what they actually are. So this is, CO is the convection number. You would compute it as shown. So it's a function of the steam quality and of the relative densities of the two phases. So you compute that. It's just you're directly computing it. Then there's this number here, which is called the boiling number. So this is related to, let's see, G. So G is the mass flux. So this is kind of a relationship between the heat flux you're providing and then like the mass flux of the system. So it kind of gets to the question about how long this would take. So sort of like a normalized representation of how long this should take. The last one, FR, is called the Freud number. F-R-O-U-D-E. Maybe I pronounced that wrong. Freude, I don't know, some German people in here. And it's basically this grouping shown here. So all you have to do is kind of compute these three values, and then you can apply the correlation. How do you apply the correlation? Well, it turns out that first you just compute the Nolinsky correlation. So if you remember back, we talked about turbulent flow correlation. So first you compute the Nolinsky result for turbulent flow in liquid phase, and then you modify that based on the Shaw correlation. So the Shaw correlation is kind of a layer on top of the existing Nolinsky correlation. That then lets you compute H bar. So for example, I realize this is hard to see, but let's assume that we had computed the Boiling number, the Freud number, and the convection number. We already have those in hand. Then we have to go through and just go through this process, right? So if you were Ease or MATLAB or something, you would, of course, have this in a function. But you compute the values, and then you say, okay, let's see, am I considering vertical tubes or horizontal tubes? Is the Freud number greater than 0.04? If not, do something else, right? Then I compute this HCB. And then I compute this HNB for all these different possible scenarios. So if the Boiling number is within a certain range, I do one thing versus the other. Or you just kind of go through these steps. Then the last thing is I have this N, right? And N we computed up here. So I have N, and then I use that to evaluate H. So it's this procedure you follow, and it just gives you back the H tilde, which you then multiply by the Nolinsky result, which gives you your convection correlation value. Okay, so obviously I'm not going to go through that in detail because it's really boring, but that's sort of how you would apply it in a real situation.